Okay, let's complete this table for 2 to the x. We're going to sketch the graph and its inverse, and then state the domain and the range of each. Now, I did not say find the equation of the inverse. That's not in this lesson. So let's complete the table, and this will be rather common sense. Let's start at the bottom. 2 squared, that's 4. No surprises there. 2 to the 1 is 2. 2 to the 0 is 1. 2 to the negative 1, we've been through this pattern in different contexts, but we're basically going to just look at this and say, well, half of 4 is 2, half of 2 is 1, half of 1 is, well, it's a half. And it makes sense. This negative exponent moves things. So we're going to plot these points. We'll plot them in blue. So negative 1 comma 1 half, negative 1 comma 1 half, 0, 1, 1, 2, 2, 4. And if you want to go even further, and you know you do, you could go 3 and then 8. That works. So we can go even further with that. We'll make it 3, 8. And so we have 3, and then 1, 2, 3, 4, 5, 6, 7, 8. There, counted correctly this time. And I will connect these points. Hard for me to say. I will connect these points because this is a true function that's not in some context like the previous problem was. If you're following along with the notes, where we had the number of flips and the amount that this person owed another person. So that had to be more discrete, countable. This is going to be a continuous thing. So we can connect these in a nice, smooth, wait for it, exponential curve, right? I mean, that's the title of the lesson, right? Exponential functions. So wonder what happens over here. And I'll go ahead and tell you, if we were to plug in a negative 1, we get 1 half. If you plug in a negative 2, you're going to get 1/4. Because your negative exponent will move things. So let's do this on the calculator quickly just so you can kind of see a point of reference for this. 2 to the negative 1, whoops, that's in the wrong place. 2 to the negative 1 is 1 half, okay? Well, 2 to the negative 2 as a fraction is 1/4. What that means is 2 squared is 4, but that negative exponent is going to throw it into the denominator, so 1/4. 2 to the negative 3rd is going to be 1/8. There it is. So whatever I do for my negative exponent, it's like I'm doing that for a positive. 2 to the 3rd, it's 8, but it's in the denominator, it's 1 over that. So these numbers are going to get closer and closer and closer to 0, basically. So I keep taking half as I go. Half of a half is a 4th, half of a 4th is an 8th, half of an 8th is a 16th, and we'll just keep going. So what that really means is it's going to be very hard to draw. Whew, I'm not doing a very good job of it because it's 1 half, 1/4, 1/8. That's not done well. 1/16, 1 over 32, 1 over 64. Almost impossible to draw by hand with this kind of scale anyway. But in a practical sketching sense, whoops, hit my x-axis there. You are not allowed to touch the x-axis, and my pen slipped right there. But you're not allowed to touch the x-axis, which really means this. No matter what number you plug in right here, you'll never get 0. Now, a calculator or a computer will eventually give you a 0. I could plug in, watch this, 2 to the negative 100, and I get, well, actually, that's not 0. That's 7.8886 times 10 to the negative 31, which is really, 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 really small. That's 0.0000000, a bunch of zeros, and then 7888. That's close to 0, but it is not 0. It'll never be exactly 0, even though the calculator will tell you it is. It technically isn't. It's so close to 0, the calculator doesn't know any better way to represent it. It doesn't have that capacity. So this will never actually touch the x-axis. There's a word for this. It's called an asymptote. We'll talk more about what that word is and what it means later, but it basically means we'll never touch the x-axis in this context. So sketch the graph and its inverse. So let's do the exact same thing, only reversing the coordinates. So instead of negative 1 comma 1 half, we'll have 1 half comma negative 1, and then 1 0, 2 1, 1, and then 4 2, 1 2 3 4, up 2, and then 8 3. 1 2 3 4 5 6 7 8 1 2 3. There we go. And we have talked about inverses before, so basically we have everything here that's represented here. It's reflected over the line y equals x. If I drew with a purple pen, you don't have to do this, but if I drew this line right here, then everything on one side gets reflected to show up on the other. This is the line y equals x. This was in the inverses lesson. It's one of the cool things about inverses. So I'm also going to connect these as well, and I need to be careful about this. So I want it to look just right. And I was not allowed to touch the x-axis on the original graph. So on the inverse, which again, I don't have to find the equation of, but on the inverse, I'm not allowed to touch the y-axis. I will neither touch nor cross the y-axis. I got to get closer and closer to it, which is really hard to do. So that is not a really good representation. So if you graph this on like Desmos or something, you could zoom in and zoom in and zoom in, and you'll never actually be on the x-axis here or on the y-axis there. State the domain and the range of each, so let's do that. All right, domain, range, f and f inverse, which again, we did not find the equation of, but we can sort of cheat on this. This is the situation where domain and range are swapped for a function and its inverse. Okay, let's look at the blue graph. That is the original function. The blue graph goes forever to the left, okay, and it goes forever to the right. Now we might say, well, it turns up very sharply. Okay, yeah, it does. That's fine. But it goes up forever, like forever, and goes forever to the right. It does turn up very sharply, but it does continue to go forever. Another way of looking at it is, am I ever allowed to plug in values of large values of x? Like, could I plug in 20? Yeah, 2 to the 20. Can I plug in 1,000,000? Yeah, 2 to the 1,000,000. So the graph does exist way over here. It's way the snot up here, but it exists. Okay, so without even thinking, let's do a little bit of cheating here. Negative infinity to infinity. See? Whatever your domain is for your original function, that is the range of your inverse. And check this out. Negative infinity, and then it goes up forever. It goes very slowly, but it does go up forever. Okay, let's talk about the range of the original function. The range, let's see, it's never going to touch 0, but it hovers above 0. So we could say that I say this loosely and kind of carefully, it starts at 0. It doesn't start at 0, but it is a place where I would begin the process of talking about the range for sure. So from 0 and up, but not including 0. And that makes sense with the domain over here because the domain is from 0 to infinity, not including 0. So from 0 to infinity. So the domain and the range are swapped.